In this video, we take a look at properties of vector addition and scalar multiplication, theorem 4.4 in chapter 4.2. So the most important reason for defining an abstract vector space using the 10 axioms from the previous video is that we can make general statements about all vector spaces. That is, the same proof can be used for Rn and the set of continuous functions on the closed interval AB. So here are the 10 axioms that I am referring to back from the definition of the vector space. So if you want to verify something is a vector space, you check all of these definition properties, all 10 axioms, as we say. All right, so here are some properties of vector addition and scalar multiplication. So V is a vector and Vn, and C is a scalar. Then 0 times V is going to give you the 0 vector. And we know that because 0 is going to component-wise multiply by each element of V. And scalar C times the 0 vector is still going to be 0 because 0 is in each element of the 0 vector. And then if the product C times V equals 0, then either C is 0 or V is 0. So this is what you knew back in algebra as the 0 product property. And then the scalar -1 times V, we just denote as -V. So we're going to prove the second property here first. So note from axiom 4, back in our list of the 10 axioms for the vector space, that V has a 0 vector such that for every U in V, U plus 0 is still U. So using this axiom, we know that 0 is going to equal 0 plus 0 because 0 itself will have a 0 vector itself. So you can write the steps below. So C, the scalar times 0 equals C times the sum of the 0 vector plus the 0 vector. And then you can rewrite that with distribution as C times the 0 vector equals C times the 0 vector plus C times the 0 vector. And then you can add -C times the 0 vector to both sides. And so what that does is on the left side, these 0 out. So then you get 0 on the left has to equal C times the 0 vector. So you've proven that the property here that C times the 0 vector equals 0, the second property. All right, to prove the third property, where we're going to show that if C times V equals 0, then either the scalar 0 or the vector is 0, essentially the 0 product rule here. So to prove this, let C times V equal 0, where C is a scalar and V is a vector. All right, to show this implies either C equals 0 or V equals 0, assume C is not 0. If C is 0, we're done. We've proven our result. So now that C is not 0, you can use the reciprocal 1 over C, right? Because the reciprocal exists since C is not 0, to show that V must be 0. So V, we could rewrite that as 1 times V. So that could be 1 over C multiplied by CV. And then we can use associativity to say that's 1 over C multiplied by the product CV. So if that whole value equals 0, then it must be that V equals 0. That's the only way we're going to get 0 out there because we've said C is not 0. Okay, the property 4's proof, you can prove really easily using the axiom for the scalar multiplication. And then property 1 we already talked about using, again, the distribution here, 7. So you would distribute through and get 0s for everything in property 1. And then you could do the same property here for 4. If you distribute that -1 through each component, you're just going to get the negative version of the vector. Okay, so here's our summary of some important vector spaces that are frequently referenced in the remainder of our textbook and the semester. So the operations are all what we think of as the standard operations in each case. So you've got R, the set of all real numbers, as a vector space. R2, the set of all ordered pairs. R3, the set of all ordered triples. Rn, the set of all n tuples. C, negative infinity to infinity, in parentheses, that's the set of all continuous functions defined on the real number line. And then C of AB is the set of all continuous functions defined on a closed interval AB, where A is not equal to B. P, the set of all polynomials. P sub n, the set of all polynomials of degree less than or equal to n, together with the zero polynomial in there. The set of all m by n matrices, and then a subset of that is, of course, the set of all m by n square matrices. So these are vector spaces we will be using and referring to. So let's take a look at some examples that are not vector spaces. All right, the first example of not a vector space is the ordered pair of integers over the field R. So imagine if you have a scalar that's a fraction multiplied by an integer, you don't have an integer anymore. So for that reason, Z2, these ordered pairs of integers, is not closed under scalar multiplication because, say, we take a half multiplied by the ordered pair 1, 2. Now we've got the ordered pair a half and 1, and the half is not an integer. So an aside on notation, this 1 belongs to Z, that E symbol that it belongs, means that 1 is an element or is a member of the set of integers. So this circular E is a belonging symbol in math. And then half is not in Z, means that 1/2 is not an element of the set of integers. So this is what you can think of as the belonging to or an element of symbol. All right, so although the set of ordered pair of integers would satisfy axioms 1 to 5 and axiom 10 of the vector space, it's not a vector space because not all axioms are satisfied. So if you're trying to show something's not a vector space, you only need to find one axiom that's not satisfied, and then you're done. Okay, what about the next example? The set of second degree polynomials is not a vector space because it's not closed under addition. So for example, if you've got P of x equals x squared and Q of x is negative x squared plus x plus 1, then you get no more second degree polynomial. You get a first degree polynomial, and when you add them up, you get x plus 1. So that's why the notation always says the set of all polynomials of degree less than or equal to n, together with the zero polynomial. So you've got to have all degrees and less. The vector space of V equals R2 with the standard vector addition, but non-standard scalar multiplication, defined by this. If you've got a scalar times a pair U1, U2, the scalar equals the scalar times U1, but 0 in the second component, that would not be a vector space. So let's look back at our properties. What would that fail under? The 10th axiom is not going to be satisfied by this set. You're not going to be able to have a scalar identity there. So the first 9 axioms are actually satisfied under this alternate definition of scalar multiplication. But if you try to multiply scalar 1 times, say, the tuple 1, 1, the ordered pair, then you're going to get 1 and 0, and that is not equal to its identity element 1, 1. So the 10th axiom is not satisfied. We don't have a scalar identity So we say that this, with the non-standard scalar multiplication, this vector set is not a vector space. Oh, and I wrote it right down here. It turns out, here's another example. The only axiom not satisfied by this case is axiom 10, scalar identity. So here's my next example. I forgot I'd already typed this. So we can see 1 times the ordered pair 2, 3 is 2, 0, which is not equal to the identity. All right, here's another example that's not a vector space. Rotations in 3 dimensions. And here we're representing them as arrows using that right-hand rule. So the right-hand rule says if you curve the direction that you're rotating, then your thumb points in the direction of the rotation. So that's the magnitude in the direction of the degrees, your thumb. So scalar multiplication is a standard operation. So you're stretching the arrow or reversing the direction if the scalar is negative. So vector addition is the first rotation followed by the second rotation. So if you're doing 2 rotations. So this is not a vector space because vector addition is not commutative. So if you first look at this box and we rotate first the front from this position to that position, angled at a different angle, and then we rotate the box around this way, where the top is now angled, then it's not the same as if we first rotate the box, so the top is angled, and then rotate this way because you end up, as you see, with different final pictures. So in chapter 6, we're actually going to see that rotations can be represented not as vectors, but not as matrices. Oh, sorry, but as matrices. So rotations, we use matrices. If you imagine computer graphics, when we design the code for like computer animation or computer graphics, we use matrices for all of the motion there. And you can imagine the 2 dimensions of the matrices let you have many, many possibilities, or even every possibility for motion in computer graphics. Okay, in the next video, we will take a look at how to check whether things are vector spaces or not. So we're going to look at some sets and determine vector space or not.